The following is a production of the University of Minnesota.
So today we have with us Professor Susan Mental and we have Professor Henry Stolarski. Did I say that right? Awesome. So Professor Sue Mental is a professor in the Mechanical Engineering Department at the University of Minnesota, and her research focuses on the design and analysis of structures utilizing polymers and polymer composites. Mechanics principles associated with design using orthotropic and anisotropic materials are also developed. One of her current research topics is in developing a wireless self-powered sensor node for monitoring the health of wind turbine blades. So Professor Susan Mental will be presenting first, and then we'll have Professor Henry follow.
Great. Thank you very much. I hate these speaker thing. Okay, and that's not going to work. No, it's really not going to work. Something just, it's fine, yeah. They're made for men who wear blazers. Okay, this should be good. I'm happy to be here. I've given this presentation before, and I think that all of you have seen the slides, so hopefully I'll be able to add something to that and make it a little bit more fun than just looking at a bunch of slides. So I'm going to speak more about materials and sort of the considerations that you would have if you were looking at a wind turbine blade. For mechanical engineers, some of this should be pretty straightforward. For double E's, it'll be a little bit new, but nothing that should stump you on homework questions. And then Professor Stolarski where our talks go well together, he'll go a little bit more into detail on how people actually model these blades and what kinds of information you can learn from that. So a lot of the motivation, and something that, how do you say your name, Muduta just mentioned, was that I am working on working with somebody from aerospace engineering and a material scientist to develop a sensor that would be, you could add it to a wind turbine blade even after it's been manufactured and it's out in the field. It would be a way that we could monitor how healthy the blade is, whether it's about to fail, like the picture that I had at the beginning of my talk. So the motivation for this is that if we looked at sort of, this chart just shows the likelihood of various components will fail. And so what you're looking at is the blue is annual failure rate, and the red is the downtime per failure. So if there are a bunch of different components in a wind turbine. The electrical system kind of is at the top for blue, and the drivetrain is the top for red. So what that means is sort of the drivetrain, that would be all the gears and so forth. If they were to fail, the downtime is a huge length of time. It would be down for many days. And that's a very common failure, is the drivetrain. And if you look at electrical systems, it's saying that electrical systems will fail most frequently. So wind turbine blades are kind of in the middle. They have a reasonable, they're not too bad. They don't fail that frequently, but when they do fail, they're down for a long time, and it could be a big problem. So I was just going to go through sort of the considerations for wind turbine blades and designing and materials. And as Muduta mentioned, my area is composite materials, so I did bring some samples that we can pass around. These aren't pieces from a wind turbine blade, but these are typical composite materials that are used when they manufacture the blades. So when you're designing something, then there are a couple of things that you want to consider. One would be, we would talk about what the loads are. So, when you're designing a table or a diving board or anything like that, you want to figure out what kinds of loads there are on that structure. And then when you're picking materials, what are some of the characteristics that you're looking for? So first, if we look at the loads, the idea with a wind turbine blade is that the loads will be different along the length of the blade. So that's what this illustration is trying to show, is that you've got wind flowing over the blade. And if you were, back from mechanics days, you have something that looks like a cantilever beam, meaning it's supported, and it would be supported at the nacelle, and it's free at the end. And the load along that blade would vary because of how the wind flows over it. And the other point that I wanted to make is that there are both static and dynamic loads. So what would be the static load here? Well, the static load would be if I had my wind turbine blade and it was out horizontally, then you might consider the static load would be just the weight of the blade itself. And then dynamic, what we can see is that as the blade is rotating, the loads will vary because of the position of the blade, right? So we've got static and dynamic. Flapwise bending, so there's something on the blade, we'll say there's flapwise, which means just in this plane, if my center of my head is like the nacelle, then flapwise is this idea that it's up and down, and then edgewise is out of the plane, so in towards the board. So you've got a pretty complex loading situation, right? It's rotating, it's got this flapwise, most of that is because of the weight. So, as it goes around, the angle that it makes is different, so that gives you different flapwise load. And then you've got this edgewise, which is varying because you've got wind speed varying. So it's a pretty complex situation. And if we add further that what people are trying to do more and more is get more energy out of things, right? So if you went back, 100 years or 150 years, you'd see these really small wind turbines, but now people are making them bigger and bigger, trying to get more and more power out. So Professor Stolarski has, I think, a slide that shows also size. And so this would just give you kind of a framework. There's the Statue of Liberty. And, one of the larger wind turbines, the tower is located 80 meters. So that would be up to the nacelles, 80 meters. And then the rotor diameter is 100 meters. So each blade is about 50 meters long. And that size compared to the Statue of Liberty is pretty large. I believe, and I was just up, on that Elos wind turbine, the turbine that we have down at Rosemount. I actually got to climb that about 2 weeks ago. So the nacelle is 80 meters up, and I believe the blades are about 40 meters long. So ours is right in this, what is it? Is it a 2.5? Right, megawatt. So that's that largest circle there. So, how do you deal with this? So one of the reasons why people have been able to make those wind turbine blades so long, what's changed over the years is that we have lighter weights, different materials available to us. So that would be the composite materials that everybody wants to use but are super expensive. So these are fiber reinforced plastics. We want to use them on airplanes because they're lightweight, stiff, and strong. So that helps you with, you don't have to deal with carrying all that weight on top of everything else. You have something that's super strong, super stiff, but doesn't weigh as much. So how do they deal with that with rotor blades? You can see here's just a classic shape. It has a supporting spar. That's that middle piece. And let me see. I think I'll have another slide where I show more of the anatomy. But you can see that the shape is changing, and this is just one cross-section, and you can imagine that as you go down the tip of the blade, it gets smaller and smaller until you have, very much smaller size tip. But in general, it maintains this sort of aerodynamic shape, just like an airplane wing would, but it has some twist to it, and it gets smaller as you move down. And it's all designed so that we've been recently looking at what are all the strains on this. People have spent a lot of time designing this and designing that twist and shape so that the strain is pretty much the same all the way down the blade. So you don't necessarily, you have one end that has a little bit higher strain, but you don't see these huge variations. So like if I took a diving board or a cantilever and supported it at my arm and it was all the exact size and shape all the way down, then I'd have much higher stresses up here. But what they're able to do is they've taken into account that loading and the length and everything else and changed the shape as they move down, so that it's appropriately sized. And again, this is why composite materials, fiber reinforced plastics are perfect for this because it's very easy to construct this and have the shape change all the way down. All right, so then some of the other features I'm just superimposing on here. So I've mentioned size and twist. Again, check out how long that is. You can see the taper. And up at the front end here is a bolt circle on where it attaches. And again, to get an idea of perspective of size, look at how big the person is. And now look at how big that bolt circle is. the person can stand inside the bolt circle. It's huge. Here's another picture, something a little bit smaller, but it looks a lot like an airplane wing, right? Except for this beginning part where they've sort of fanned out and then made it bigger about, maybe, 10 meters down the blade. And they figured out all of that geometry based on just getting the loads and stresses to match up. Here's just a whole stack of them. All right, so in terms of desirable properties, I could put this list down for any time you wanted to design anything out of composites. So, we just look at this rotor blade as something that we're designing out of composites. And these are some of the features then that I would go through if I were designing something from a composite material. Size, weight, stiffness. What does it mean to be stiff versus strong? Okay, so stiff means that it doesn't bend very much. Strong means it doesn't break. Okay, so there are two different features. Sometimes, especially in composite materials, you can get something that's stiff, but then you have to check every layer. So when they're making that composite, they'll build it up layer by layer, and you have to check every layer for failure. So you can make something super stiff by like putting a big core in there, but it may not satisfy the strength requirement. Complex shape and long fatigue life. So what I want to do here then is go through some classic ways that we look at material properties and just show you how you end up picking a composite for this part. So these would be the modulus. And again, how many people here are MEs, by the way? Okay. How many people are double E's? All right. Okay. And how many aero? Civil. How many civil? Okay. Chemical engineers? None. All right. So civils, you guys all know about structure stuff, so this should be pretty easy. Double E's. Have you ever heard of modulus before? Okay, good. All right. All right. So I'm good then. How about fracture toughness? Anybody want me to explain fracture toughness? Okay. So fracture toughness is pretty common in polymers, especially. People worry about how much load it can take before a crack grows. So fracture toughness, something that has a high fracture toughness, actually would be not very brittle. Something that's brittle has a very low fracture toughness. So it kind of works opposite. So in composites, there's always this trade-off. You want something really stiff, but you want it to be tough. You want it to be sort of resilient to breaking. So we'll look at properties. So these kinds of properties that we're looking at are fairly this is a classic chart from a book by a guy named Ashby, A-S-H-B-Y, and he is a British mechanics type of person, and he figured out different ways of looking at material properties so that you can kind of compare things. So in this plot, then he's got Young's modulus and density, and then what he did was he just put all the different types of materials in there, and what you can see is that, so if we go through it kind of slowly, let's say wood and wood products don't have a very high modulus and they're pretty low density. You can see where composites are at the sort of top right corner. So those are high on the stiffness and kind of a medium density, not too heavy. If you look at ceramics up at the top right, that would make sense then. They would be very stiff and kind of and heavy, right? So there's some trade-offs. So what we do, so here's a bunch of lines on there. So if you were thinking about, there's a kind of a thing called a merit index for a beam, all right? And so the idea is you would like the lightest weight beam that won't deflect very much. So this is the idea. You want it to be very stiff and you want it to be really lightweight. So if you took some factors, you'd say there's density then. So you'd like kind of a low number of density, and you'd like a really high modulus. And so here then, what they've done is we've got some lines that sort of frame what would be reasonable for making a, let's see, I would just want to add this one more thing to it. What makes it sort of reasonable to pick a composite? So we've taken the red line and said it has to be at least this stiff. Okay, that means, you know, I have to have a certain amount of stiffness because I don't want it to deflect very much. And then in terms of these green lines, what we've done is they've said, take density and divide it by the modulus to the square root, and that has to do with deflection of a beam. So that's how they come up with this rho over modulus to the square root. Has to do with something like the deflection of the beam, and that's that merit factor, and that frames the two green lines. So that's how you get this slope. Notice this is like on a log scale, so that's how you end up with those two straight lines. So you've said, I want to be between the two green lines, and I want to be above the red line. And then that's how you end up with saying a composite material is one of the best. The CFRP and the GFRP. So CFRP, that is abbreviation for glass fiber reinforced, and then CFRP is carbon fiber reinforced. So basically, carbon fiber reinforced plastics have a different stiffness than glass fiber reinforced, and some are better known for their strength. So carbon fiber reinforced are higher on the stiffness category than glass fiber reinforced. Let me think if there's something else I want to say about this. I will show some samples in a minute, but I'll just keep going. So another consideration that you would have if you were designing would be strength versus toughness. So you want something to be very strong, but you also don't want it to fracture and be brittle. So here's another one of these kind of multi-material charts. Strength is on the vertical axis, and toughness is on the horizontal. So if we want something really tough because we don't want cracks to grow, then we want to be far to the right. We want something super strong because we don't want it to break. So then we want both the combination of high strength and toughness, and that's where composites come out pretty good. If you look at, ceramics and glasses are on the top left corner. What you see there is that ceramics then would be very, very strong, but very brittle. So that's sort of, if that helps you kind of think about where composites fit in, they've got the strength and they're tough at the same time. All right, so that's all I wanted to kind of go through on general material properties. So we've talked about stiffness, density, strength, and toughness. And of course, everything says you should do a composite, but a lot of that also is because composites are easier to work with too, and that's not something we've talked about, but in terms of making the shapes, they'd be a lot easier to work with. They're not so easy to manufacture, you know, in terms of getting the shape, but you can make the shape that you want. So, like if you want to make a wing out of aluminum, the problem with that would be it would be kind of heavy, and it would be, it's difficult to make that twisting. So we can see airplane wings are made with the shape, but you don't see all the twisting going on, and so composites lend themselves to that. So I'm just going to go through a few slides showing how somebody makes something out of a composite, and I brought some samples of some of the materials. I feel like this is missing a few of the slides that I had. That's why I'm thinking, but it's okay. I mean, I should be good. I was thinking, well, it's all right, because I'll just keep going. I went through the talk before I came over, and I was like, I'm missing a couple things, but from I didn't look at those. I just looked at what was on my computer. It's fine. All right. So anyway, these are the layers. So let's just say, so I'll pass out some samples, but when you're making a composite, you get a choice on directions, and this is the only reason why people, this is the biggest advantages that composites offer. So composites have this possibility of being directional. What I'm showing here is that let's just say you had 3 plies. So that's what you're looking at. The lines represent the direction of the fibers. So if you want to make the lightest, stiffest part that you possibly can make, then what you'd want to do is orient the fibers and not get, so you can make it where the fibers go in every direction, but that would not have any weight advantage whatsoever. What you have to do is be smart about how you make that composite wing. So if I'm making a blade or a wing or whatever, and it's deflecting this way, then my preferential direction for the fibers would be like from my shoulder to my fingertips, right? Because the fibers are the strongest part, and so that would be the ideal way to make the fibers. And there would be, like if I didn't have any weird twisting thing, there'd be no reason for me to put fibers in any other direction. So you agree with that? So this is how you make the lightest weight possible blade that you can, and this is why you'd like to be using composites for something like this. If you used aluminum, well, you don't get any directionality with aluminum, so you get great properties in every direction, but maybe you didn't need them in every direction. So that's the beauty of making something out of composites, but that gives you the expense too, because then it's a kind of a laborious process, right? You got to put layer upon layer. You have to figure out what direction you want those. So you'll start with something. This is like an old decrepit piece of composite that I had in my office, but basically it'll come out like a sheet. You buy it. You can buy it in a big roll, and if you use what's called a pre-impregnated composite, it has the fibers and the resin all put together. So it comes all put together, but the problem with that is that it has to sit in your freezer until you're ready to use it. So like Boeing literally has big freezers full of composite material, and they've got 2 layers. So you're seeing the pink side, and then you'll see on here, this is a glass fiber, so it looks kind of whitish. But basically, it comes in a big roll, just like contact paper, and then I take it out of the freezer, I let it thaw for an hour or so, I unroll it, and then I can peel this layer off. And it's still kind of sticky. Put the next layer down. So you just keep laying it up. And then you'll take it. You'll apply, here, I'll just keep going here. So you'll apply heat and pressure in what's called an autoclave. But basically the idea is that all those layers are individual and you sort of tacked them in place and they're sitting on each other. But then what you'll have to do, you have to basically cook it. You have to cure that resin. It's a resin that cures at like 350 F usually. So you'll put it in an oven, you have to apply pressure, so it's usually an autoclave where that's a way that you can bag it and then you'll put an external pressure on it. So to make the composite, you have to put the layers down in the order that you want. You have to have figured out what order you want them in and apply heat and pressure. That's what you do if it's a pre-impregnated material, meaning it's got the fiber and the resin all together. I'll show you another technique where you just put a bunch of fibers down and then you squirt resin in. Okay? This pre-preg technique is the most expensive way to make a composite, but is the best control you're going to get over the fiber and resin content. And the thing is, if you want the ultimate properties, then you want to control how much resin you have. You don't want too much resin because it just adds to the weight, doesn't help you with strength at all. It's just a bunch of plastic, right? You need enough resin to keep all the fibers in place and keep everything together as a part. But if you have more than like 50% resin, so 50-50, then you're not getting the optimal characteristics. It's still better than anything else you're going to get. So that's why people go for the pre-preg. I'll just say that it's pretty tough to make, and I don't think I've ever read that they make wind turbine blades from a pre-preg. But if you're learning about composites, then this is kind of the classic, the ultimate, the standard. They will do pre-pregs on airplane wings, but they won't do it on a wind turbine blade, and that's because it's just difficult to get all of that shape in while using a pre-preg. So I'll show you how they do that in a minute. On this slide, I'm also showing that they'll add a core material. So this is okay. You have a top view here too. Maybe no, should be right. Yeah. All right. Okay. This is honeycomb core. It really looks like honeycomb. And it comes in all sorts. Like this is actually a cardboard honeycomb that's got some kind of resin on it that makes it stiffer. There's also aluminum honeycomb. And Hexcel makes all these different honeycombs. You pick it out. It's based on like the size of the cell, the thickness. You can get all sorts of properties. Cool. Isn't that neat? All right, so you can sort of see it's mostly air. All right, that's good. Go back to the thing. Perfect. So at any rate, this is the honeycomb. So the idea is, if you want something really stiff, okay, civil engineers, just like I-beams, right? So with the I-beam, you have the flange and then you have the webs, right? And the idea is that you want those webs far away from the neutral axis so that you get something really stiff. And that's what this core does. Basically, it takes these 2 sheets, moves them further away. So, yeah, this is where I probably, okay, you guys ignore me for 1 minute. Talk to your friends while I look through these slides really quick. Okay, good, I do have it. All right. Okay, so I'm going to skip one slide and go to the next one. So the idea with this core is it gives you some stiffness and it helps move those sheets away, and you don't have to use as much composite material, right? So you're trying to be cheap. Now, you know, the ideal thing is you just keep beefing up the core because it would make it stiffer and stiffer, but you need enough layers so that these layers don't fail. You know, if you move them out, they get a high stress on it. You don't want to, you need enough layers so that you don't have that failure, that strength failure. Okay, so here's where I was talking about the trade-off of stiffness and strength. So I can make something super stiff by making a lot of core and not having too many layers. I can definitely get the stiffness, but then the stresses in these layers would be too much, and they would fail from the loads itself. You'd have a strength kind of failure. I'm going to skip this slide and just show you something. So this is my anatomy of a rotor blade. So basically, when you're looking at the blade then, what will you see? So this is the picture, but let's look at the graphic. So you'll see those reinforcing kind of interior webs, let's call them. And then they actually use balsa wood and foam. So, you know, I've used the honeycomb core here, but they'll use balsa wood and foam to so there'll be balsa wood and foam, and then there'll be these layers of composite material on the outside of that. So that's how they'll make their laminate. So they'll have a laminate where it's composite, balsa wood, composite. And if you look at some of these sections, it's pretty sophisticated. Like right in the joint area, it'll be beefed up. And then it'll be thinner in other sections. They really have spent a lot of time optimizing this so that it's super lightweight. They are always using glass fiber composites. Let's go back really quick to the slide so we can see why that would make sense. So back on my slides where I picked composites and it discriminated between glass and carbon. So there we can see that glass fiber composites are a little bit lower on the stiffness category, but the same density. One of the reasons there is that carbon fiber is much more expensive, and so a glass fiber is going to be cheaper, and it will still give them a very lightweight product. And I guess they get around the stiffness because they're building up various middle sections with the balsa core, something like that. So they don't need the ultimate that you get from carbon fiber. Let's see. In this plot, we don't see any difference between composites. They don't discriminate, so we can't really say what's the deal there. But here, if we look at this plot, we can see carbon fiber versus glass fiber versus aluminum and steel. So if we're saying, well, okay, we're trying to build up that shape. One plot on the left shows specific strength, and on the right shows specific stiffness. So what you're looking at is you're taking the strength and dividing it by the density, and you're taking the stiffness or the modulus and dividing it by the density. And you can see that in terms of specific strength, carbon and glass fiber just far outwin aluminum and steel. On specific stiffness, you know, you don't see much of a difference between the glass and the aluminum, glass fiber composites and the aluminum, but still, you know, we've got a real benefit on this on the strength side, so that's one of the motivations. All right, I haven't talked a lot about the resins. I'm going to skip that for a minute. So here we're looking at our rotor blade. We've got the cross section, and it's definitely a highly engineered cross section. This is not something somebody just slapped together. They've thought a lot about, you know, where they're going to add material, how they're going to stiffen it. Balsa wood is just nice to work with because they can taper the shape. It's not so easy to just taper this honeycomb, plus it's super expensive again. And you know, these wind turbine blades are really long, and they're trying to save money as best they can. So here then is a schematic of a process, and then I'll show you some real figures. So I talked earlier about how I could make a part by using prepregs, but the other choice is to use something called vacuum-assisted resin infusion molding, VARIM. V for vacuum, and R is vacuum-assisted, and then resin infusion molding. So what happens here is you've got, and this is how they make, this is actually a cross-section of a boat hull. So this is how they'll make boat hulls, and this is how they are making some of these blades. So they'll have a mold, so the gray is the mold, and then there's a bunch of layers. So you'll see laminate, then there's the core, then there's another laminate. So the next 3 layers, right? So starting with the mold, and this has the outside shape that you want your part to have. So in this case, you can envision that does look like a boat hull, sort of, right? Okay, so it's huge. And this is the way they're making big parts. So basically, and then after you put all of those layers in, so you've got laminate, core, laminate, right? So it's like a sandwich. Then they'll have a bagging layer over the top. So that is going to seal it all in. And they're going to, so they've got, you can see the vacuum bag, right? And they're going to pull a vacuum. And at the same time, they're going to inject resin. So it's going to flow through. So that laminate really is just fibers laid up. And a lot of times the way they'll do that is they're not going to have unidirectional fibers, so it's not like super optimal, but what they'll do is they'll make a weave. So they're using the same technology they use to weave fabrics, socks, anything like that. So they have a weave that creates what's called a preform. And that preform has kind of preferential direction of fiber orientation. They'll put that in there, and then they'll just inject the resin through. And it happens. Happens very quickly. I think they can make the whole part, injected through in a day, because basically that resin is liquid, and as it goes through, it'll react, and you'll get the reaction happening. And so you can't just, oh gee, I'm going to wait for the resin to get everywhere I want, and then it'll start to react. They really spend a lot of time figuring out where they're going to have those injection points, how much time it's going to take. They don't want it to solidify before everything has filled the mold. So that's sort of tricky. So here's a slide showing, and so one technique that they use is a clamshell mold. So that's what you're looking at here is, imagine that blade and you cut it in half just like a clamshell. Okay, so here then, there's the mold. Look at all of these locations where they're injecting. It's not like they just go at one end and they eject at the root and then go all the way down to the tip. They basically have figured out various pathways. They've done computer models to figure out how the resin is going to flow. They often, back when I first started working here at the U, there was a big study on race tracking, which is where you've got all the fibers in one area, and then you might have some areas where things can go through faster, and that's what they would call race tracking. So at any rate, and some of the work here, it was just a huge body of work on figuring out how to lay these things up and get the resin to go everywhere you want. And you can see how big they are, how intense it is with the labor. There's a bunch of people there. And once you lay this up, you have one shot at it. If you mess it up, it's a big pain to find your flaws and repair them. So they really work hard to get this right the first time. Here's so another figure showing some of the finishing steps. So basically, then they'll make one half of that shell, and they'll lay in all of the interior webs. Those will help you with shear stiffness. So shear is kind of loading where you take something and you'll load it, and shear means you'll load both sides and it'll shear kind of, how do you describe shear? So shear, double E's. Do you guys know what shear is? Okay, good. I don't have to describe that. All right. And I know civil engineers all know what shear is and webs and everything else. So this should be an easy assignment for you guys. All right, and then they'll put the two blade halves together. And then there's a huge amount of work that goes into surface smoothness because it is an aerodynamic blade, and so people are really concerned about what the surface looks like. All right, and so basically one of the things that we've seen then is with all of this manufacturing and using composites, this is why the blade lengths we've been able to make much longer blades. I don't think this was possible a long time ago, back when they had the small farms and those just little metal wind turbine blades that you see that are really tiny. But now that we can make things out of composites, we can make the shape, the aerodynamic shape that we need. We can keep the weight down. You notice at the tip it's much, much smaller. The weight is very small, so you've got all the weight kind of concentrated closer to the nacelle. So there's huge advantages. Okay, now I'm just going to take a second and pass out some of these things so that you guys have a few things to look at, and then I'll go on to health monitoring. So I brought the honeycomb. Then I brought some panels too, so I'll go through everything I brought, and then I'll pass it around. So There's the honeycomb. I'm not going to pass around my decrepit sheet of example of prepreg, but these are some parts that we made in the lab. So again, it's black, so that's the graphite. Don't be deceived. Anytime you see something that's composite that's black, doesn't necessarily mean that it's a graphite composite. People are very tricky. They can put carbon black in the resin, and then it'll still look black. So, it doesn't always mean black isn't always not glass. But this one is carbon. And when you look at it, some of the things I want you to notice is amazing surface finish on it. It's really smooth. We just made it in our lab, but basically, with a composite, remember you always have that resin flowing. So whatever surface the resin touches, it's going to take on that shape. So here we had a very highly polished mold. So when the resin, it's liquid and it's just touching that mold surface, it's going to come out just as polished as the mold. Now if you look at, let's see, and I think the camera can, so I'll pass out another one. And on this one side is kind of bumpy and the other side is really smooth. And that's because when we made this part, the smooth side was down on a very highly polished mold. This side that's all bumpy, we had something called a breather cloth down. It was just the way we made the part. But it was like a fleece type of material. And so when you peeled it off, it kept that kind of bumpy shape. So you can get really interesting shapes. So next time you look in a car, those aren't all composites, but at any rate, just thinking about plastics, like if you look in a car, they spent a lot of time in the old days making it look like vinyl or some other surface finish. And all that is that they take a mold and they make the kind of surface that they want. And so then your plastic, whatever it is, takes on that finish. So there's other finishes that we've tried to get where we'll have something that looks kind of like woven, like it could be even like your fabric on, we'll use like a woven fabric, and then we peel that off. It has like the grid of the weave. All right, so I'll pass out. Here's a very dense glass fiber composite. If you look at it, you'll see some black things in there. That's because we, at one point, were embedding strain gauges or something like this, and we were looking at that. Here's another one. I'll pass this to you. So all of these three that are nice, smooth surface finishes and look kind of, you can't see anything, these are all unidirectional prepreg composites. The one that's a small square, when you get that, you'll see like a fabric weave in there. This one was made by taking a fabric and laying it down and then just, like one might do with a boat dock. So you've got some liquid resin and you're just painting down the layers. That's what was happening here. This probably has very low fiber volume fraction. So one of these, let's see, when you get the one that's, you'll see that it cracked. So don't feel bad. Somebody was playing with it. Now you can tell which direction the fibers were in, right? So if I bend it this way, but somebody bent it this way against the fibers and it broke. All right, so I'll pass these out. And I'm not going to pass out any of the raw materials because, so here's just an example of, this is carbon fiber woven, and the edges are taped with blue tape, but basically the fiber's almost like hair, and if you get it in your finger, it's like getting a sliver. So you don't want to get that. It's kind of a pain. All right, everybody stand up, talk to their neighbor for a second so that you're all awake, because I just have about 10 more minutes to go, but just do that for me. Yeah, take advantage of this second to just sort of refresh yourself. You can ask me after. How's that, though? Because otherwise, I just find, it's hard. It's the end of the day, and I'm probably about like 2/3 or even more through. So I just have a little short part to go. And all right. So that, I was hoping there to just kind of give you a flavor for why composites are good, what kinds of structural considerations you would have if you were making a blade, but you're not going to go out and design blades. And just to give you an appreciation for how big they are, and that people have spent a lot of time engineering these. And in spite of spending a lot of time engineering, we still get catastrophic failure. And that's because, well, first of all, that manufacturing process, you're making a big thing. It's hard to ensure that you don't have a defect somewhere. And you can have a defect in some place you don't plan on. And so there's really no way to be sure that it's going to last forever. And unfortunately, it's not like your car. Usually, you have a failure, but it's not catastrophic unless the whole wheel falls off, something like that. So, at any rate, this is why there's a lot of research being done on something called condition-based maintenance, structural health monitoring. All of these are terms that just have to do with, now that we have tools like sensors and people can make up control algorithms. So think about, what if we had sensors all along the blades, which is what we have at our station at ELOS. We actually have these really neat fiber optic sensors. They sense strain, and you can get it all along the blade. One real simple algorithm could be to just compare the sensors. If you had one on all three blades, you could just say, are all three blades giving me about the same strain? Because if they're not, maybe there's a problem with one of them. Like one of them is just bending way too much. It's just some simple algorithm like that. So these are kind of things that are available now. And if you knew that something was going poorly, sort of like your check engine light, if you knew that something was going poorly, maybe you'd be able to stop. So I am just going to put just a couple of examples then of, so Honeywell in town here has a huge group that works on this condition-based monitoring. They use all sorts of algorithms, so CBM, condition-based monitoring, and a lot of that is focused on the gearbox, because gearbox failure was one of those ones that had a very long shutdown time. Doesn't occur frequently, but shuts down. In fact, I heard that we had to replace our gearbox already at the one in ELOS, the one that you're going to visit. So it's not uncommon, and it's a pretty easy part to replace, sort of like replacing your transmission. It's not like it's cheap, but it's pretty easy. They have this huge hoist, and they hoist it up to the top, and then they'll just replace this box. So at any rate, so some of the features then that I'm showing in the slide would be then, here's things that you could monitor. We have fiber optic strain sensors. We're getting all sorts of data. We're not actually doing anything with it yet, but that's one of the unique things that we have by having. Our wind turbine is basically like a lab instrument. So we can collect all sorts of data. So we have fiber optic sensors in the blades. In the gearbox, they actually have accelerometers and tachometers. So accelerometers are basically listening for things to happen. And the generator, they can look at current and voltage. And again, all of these, there's a lot of interesting engineering that happens. So basically, we have all sorts of data then. If you look kind of further out, we have data that tells us the temperature, the wind speed, and so we can sort of say, well, given that wind speed and these conditions, do I expect the gearbox to be behaving this way? So there's some modeling that goes on, but there's also some kind of, getting a lot of data and then figuring out what's out of the norm. There's all sorts of algorithms that they use. So they'll take all that data. There's in our wind turbine, there's actually a wireless station way up at the top, and then what they'll do is they'll transfer all that data down via cable. So there's a lot of data that's gathered wirelessly up at the top, but then the rest of the way down, it's just hardwired to some major computing stuff over at St. Anthony Fall Lab. So that's a lot the basis for condition-based monitoring, and then here's just sort of a schematic. Then you've got sensors. You have some kinds of algorithms, some models of the system. So I'm working with someone in aerospace engineering who's a controls expert, working on developing algorithms for evaluating all that data. You need somebody who knows a little bit about mechanics so that you can figure out what's expected. But then you need somebody who understands about how to take lots of sensors and figure out what it all means. Because there's a lot of data out there, but it's difficult to process it all and interpret. So here, I'll just say a few words about blade health, and then I'll be done. So, because that's sort of my thing then, is about the blades. And here, I'm just saying, okay, well, where do you expect it to fail? If it's a wind turbine blade and it's like a cantilever, you're expecting the highest stresses at the root. The problem with that is that usually it doesn't fail there, it turns out. Of course, that's because they've already figured out the highest stresses are at the root, right? So they've changed their cross sections everywhere to make it just so that it shouldn't fail anywhere. So where it fails is usually has something to do with where there's a flaw, something like this. That's the thing about these kinds of failures. They're not very predictable because they've spent so much time designing that, it's not going to fail where you expect. But at any rate, what kinds of sensors? So if you have a quiz question, where do you expect failure? It's true. Probably the place you should write the answer to is at the root. Okay, that is where you should expect failure. The reality is it doesn't fail there because of all of the design work that's gone in. Okay, so at any rate, there are people who are working on sensors and figuring out where to locate them. So this is just an example. Some people have used strain gauges, and then they would put them, along one axis and then across different spots. This is just showing an example of where somebody would put sensors. In ours, we actually have fiber optic sensors, and those are pretty interesting. You can take one fiber optic line and put it all the way down the blade, and you can get, I can't remember how many we get, but 10 different locations off of that one line. Because what they'll do is they take that fiber optic line and they clean off one section, and they'll put some grading in there. So they'll put some very fine lines, and what that does is it sets up a resonant frequency. So the light goes through and it'll reflect off those lines at a certain frequency. And then if it strains, the spacing between those lines changes, and that changes the frequency that the light responds. So you got this fiber optic. They put a grading in there. Grading just means some lines. They've etched them in. It's very precisely controlled spacing. They send light through, and that has a certain frequency to it. And when it pops back out, if it comes, that's how they know which sensor they've hit based on what frequency they've pulled it back out at. And then if the spacing changes and the frequency is shifted just a little bit. And that's how they get strained with these fiber optic sensors. It's really cool. It's a really interesting technology because, so you can imagine, if the fiber is going all the way along, they've just cleared out different spots all the way along, and each one has its own unique frequency. So that's how they can get like 10 or 100. I mean, if you talk to the guys who make those fiber optic strain gauges, they said they can get like 100 off of one line. But I think we only have about 10. So at any rate, strain gauges are kind of crude at this point when you think about that. But so here's just somebody who's done a study. There's a place in Colorado where they're actually studying and looking at strain in these blades. They have a giant test set up that they grip one end of the blade and they move the other end, and they're moving it like 3 meters. The tip of the blade is moving a huge amount. It's not like it's moving, 1 meter. It's huge deflections, and then they're gathering data. There's various types of data that they'll look at. And here's just one that I'm just showing. So there's acoustic emission sensor. There's those strain gauges. Acoustic emission is just listening for sound again. Strain is what we've talked about before. And here's just sort of my last slide. So I was just trying to give you a flavor for what you could do as an engineer in terms of all sorts of things with controls and structures and sensing. That's why you can take a class like this and have double E's and civil engineers and aerospace engineers and MEs all in one class. So the goal is to avoid maintenance, to avoid having somebody actually hanging from one of these blades. And there's a lot of economic benefits then to this CBM. Remember CBM, condition-based maintenance. It has to do with looking at the condition and then maintaining it based on that. So here we are. There's a lot of economic benefits. If you can do condition-based monitoring, there's early fault detection. You can avoid costly repairs if you can find the fault before, right? What makes it costly is all that downtime. So just imagine, what do you think about when the power shuts down, right? If we were totally dependent on wind energy, then we would really like to anticipate when we were going to shut down our wind turbine for repair, right? It's just like, if you knew the electrical substation was going to shut down, then they plan on that and they send your power needs over to some other substation, right? So we need that same, if we want wind energy to be adapted by all sorts of other groups. We want to make sure we have that same predictability of maintenance. We can't just say, oh, gee, the wind turbine's down today, so sorry, you can't run your refrigerator, right? So that's the motivation. Okay, that's it. And a few minutes for questions, and then Professor Stolarski will start. Okay? Yes? Peter Seeler. He came from Honeywell, I think, so he's really got quite a background in monitoring and looking at faults. Prepreg stands for pre-impregnated composite. So it's a pre-impregnated sheet. It has the fiber and the resin put together. Everybody already probably saw the slides ahead of time. Okay, that's fine. And I'll be here after Professor Stolarski's done, so if you just have any questions then, that's fine with me too. Great. Enjoy the break.
And moving on to the second part of today's lecture, we have Professor Henry Stolarski with us. He has his master's degree in mathematics and engineering mechanics from the University of Warsaw, Poland, and the University of Illinois at Chicago. And he did his PhD in engineering mechanics from the Institute of Fundamental Technological Research. He has spent most of his professional life teaching mechanics-related classes, conducting research in the areas of mechanics, and he has been affiliated with the Technical University of Warsaw Institute of the Fundamental Technological Research, Northwest University, and University of Illinois at Chicago before he joined University of Minnesota in 1989. In the past 40 years of his professional experience, he's worked in the areas of mechanics, particularly structural mechanics. Last 30 years, he has devoted to the development and application of computational methods in the analysis of various problems in mechanics, problems of large elastic deformations, where computational methods are practically the only means of finding a solution to important engineering problems, and that's this area of interest. We welcome you, Professor.
The problem that I will be talking about is on a certain level quite intricate, and I would like, given the diversity of you, I would like to relate to something that you all know, basic physics, starting with that, and then we'll generalize it to a little bit more complicated models. First, why structural analysis is needed in this kind of applications. You realize that in order to come up with the dimensions and with the material properties that Professor Mantel was talking about, you cannot build an experimental turbine and then perform some tests on it, and if it doesn't work, build a new one, as long as it comes out to be satisfying your requirements. All this is done on a basic level analytically, using various models and using data that, including the data that Professor Mantel was talking about material properties. So this is one purpose of structural analysis, that you have to use it in the design process. But even when you have already a design turbine, or any structure for that matter, you need to have some sort of information of how a perfect structure should behave in order to, say, perform a health monitoring. You have to measure something and they compare it to something that you would expect should happen in a perfect structure. So there are various applications of that, and I will try to mention some of that. So the goal of this presentation will be to give you an outline of basic techniques that is used in analysis of structures, and then give you some applications of some example of real calculations, and then mention a little bit what has been done in the world as far as analysis is concerned, what tools are available to analyze various structures, but wind turbines in particular. Page down. Show me that. Okay. Yeah. Okay. Yes. Right. So, Professor Mantel was talking about loads. I kind of illustrate this on a complete little size of the turbine model. So we have gravity loads, and those, they are always vertical, but relative to the rotating blade, they are changing their position. So essentially, they cause time-dependent loading. And one of the most dominant, most important part of the load is the wind load. This is why the turbine rotates, and it also causes a significant forces within the turbine. So the goal of analysis is to compute the formations and the forces within the turbine. These forces are really the cause that cause a failure of different sort, fracture or rupture of some sort. So special considerations concerning loads as far as turbines are concerned are gust, wind gusts, storm winds, turbulence that is caused by presence of the structure in the flowing wind. Earthquake loads in some areas are important. Many of those turbines are erected in California, which is very earthquake-prone area. For turbines that are located in the offshore areas, waves of the water is an important loading. And one of the critical aspects in this case, as opposed to some, say, civil engineering applications where the loads are pretty much static, in this case everything is time dependent, so dynamics problems have to be considered. The effects of loads on the turbines is primarily manifested by the presence of so-called stresses. Stresses at any given point or any given plane cutting through that point of a structure are forces per unit area. I think that's for the benefit of electrical engineers that may not know the definition of stresses. So, and as you can see, this is a representative cut of turbine blade, but if you make this cross-section circular, that could also be a tower itself. The structures that you see in turbines are so-called thin wall structures. So they have a skin of certain thickness, and the skin is small comparing to other dimensions of the turbine, a cross-section diameter or the length of the turbine. And the stresses that are dominant in this case are the stresses that are indicated here. So if I make a cut perpendicular to the axis of that blade or parallel to the axis of that blade, there will be some arbitrary force applied to this that can be resolved with respect to the tangential and normal direction. So we have normal stresses and tangential stresses. Those tangential stresses are the shear stresses that Professor Mantel referred to. So the idea here is to compute those stresses because those are responsible for many critical events that can take place in a turbine. So goal of analysis is to, for given geometry of the turbine, for given wind speed, for given weight and given position of the blade, compute these values that are changing in space and in time. So what are how the stresses that we will be computing later on are used in the analysis? To predict rupture, for instance. Rupture is kind of reflecting what Professor Mantel was referring to as strength, that for a given stress level, the material may rupture, may lose its kinematic compatibility. And typically, this is described by a special material property, that is the maximum stress that a given material can take safely. So the effective stress, this is the stress that we compute due to the given load, has to be less or equal to the given material property on the right-hand side, which I call sigma strength. So this is a maximum. There are other possible failure criteria. I've seen turbine blades that fail that way, without rupturing, without creating cracks, creating discontinuities. And that's buckling. So what can happen is that the material, I will illustrate those on subsequent slides. I just outlined those. So this is also related to the stress level at a given location of the blade, but it's also related to geometry and material properties other than strength. For instance, Young modulus or modulus of elasticity. And finally, that is particularly important for turbines is fatigue. Fatigue occurs when the loading is oscillating and repetitive, and that's, of course, it's always true in the turbine structures. And what happens is that if the load is repeated many times and oscillates, there is a gradual accumulation of tiny cracks that eventually coalesce and may produce a dominant crack. And that can happen even if the stress level is significantly less than what is needed for rupture. So it could be for much lower stress level for oscillating loads. So an illustration of rupture is here, indicated by these green lines, incline. Suppose that this is a composite materials with fibers aligned with these green lines. So if the stress reaches a certain critical value, what typically happens is some sort of discontinuity, a crack along the lines. You have seen on one of these samples, somebody tried to bend this sample in the direction not aligned with the fibers, but perpendicular, and the crack developed along that line. So this is a model of a rupture. This is a cartoon that represents a rupture. On the buckling side, this is what happens here, is that there is no rupture, there is no crack created, no discontinuity in the material. But all of a sudden, for certain stress level, there is a wavy pattern developing on the surface of this. And that is buckling. So you can lose integrity of the structure, you can lose its functionality if something like this happens. And that can happen also for stresses much lower than the ones that cause rupture. That depends on how thick the wall is, how large the diameter it is, how long the blade is. So all that has to be taken into account. Fatigue is, again, it happens for a certain level of stress. If the load is repeated many times, as I said, there is accumulation of damage, micro damage, that eventually cause a failure. And that happens for stresses which are significantly less than those that cause rupture under static conditions. So that is a very important consideration for the wind turbines. So now, how do we compute these stresses? And I have another cartoon here that relates to something that you all should know from physics. And that is a simple mass with the spring, restraining motion of the mass, and some active force F of t, that produces deflections of this mass. I assume that there is no friction, so this is a so-called free body diagram. These are all forces that are applied to this mass if I isolate it from the surrounding restraints in the form of a spring or this surface, no frictional surface. And if I project all the forces in the horizontal direction, this is the second Newton's law that says mass times acceleration must be sum of all these forces. And K times U is a spring force. K is the stiffness of the spring, and it is proportional force proportional to elongation of the spring, which in this case is equivalent to the displacement U, because the left end of the spring doesn't move. So for a given, this is a differential equation of second order with respect to time. And for a given input F of t, I can find, and for given initial state, I can find the solution to this problem. So how is that related to the turbine? Mass is the mass of the structure, of course, right? Not, it has to be modified, of course. This is not a model for the turbine. This is something that I will be relating my turbine model to. So mass is a mass distributed along the blades and along the tower of the turbine, including nacelle. Stresses are represented by K in this case, by S. So K is kind of like the properties, elastic properties of the turbine towers or blade. And F of t, this is either gravity forces or wind forces that are applied to the turbine. So those have to be computed in some way. So this model will have in mind when I will be talking about much more complicated story that, that has to be told when you're analyzing structures, real structures, turbines. So in this particular case, what you can do is try to find a simple solution of the problem in the form. So if I don't have forcing term, F of t, if I don't have external load on it, and if I assume that my displacement is equal to some constant capital U times sine omega t, then it turns out that this equation reduces to equation that is here. Since sine omega t, it has to be true for any time t. Since sine omega t is not equal to 0 for all times t, then in order for that to be true, I can compute omega. And that omega has to do with the frequency of the vibration of the system, if I know this. And there are analogous models for many other vibrations in electrical systems or some other systems in the same equation. So one thing that we, for instance, want to avoid is that wind turbine has also certain frequencies for vibrations. And if the wind speed is reaching certain critical value, you may have excitation at the same frequency as natural frequency of the structure, in which case you have resonance, so-called, and there is a magnification of the deflections and the displacements, and the stresses, because stresses are related to the displacement. So we need to know that in order to, again, predict certain situations that can be devastating for a wind turbine. Now, in terms of a real situation for the turbine, what you have is this F. This mass is surrounded by a flowing either fluid, either water, say, if this is a hydro turbine, or wind. So what happens is that this F is the result of the flowing fluid around it, right? Air or water. And as a result, F is dependent on the velocity of the fluid and this dependent also on the displacement of the block mass. So you have to solve the problem that couples the equations of fluid motion and structural vibrations, structural motion. So how this is done in a real situation? In a real situation, of course, I don't have one quantity, one displacement, but displacement of the tower varies with the length of the tower. Displacement of each blade varies along the weight of the blade. So I have to deal that and take into account this variation. So typically what is done is that this nacelle is analyzed as a rigid body, and you have deformable tower and deformable blades. But the blades are kind of not rigidly connected to the tower, but they are rotating, of course. So you can, this is in the terminology of mechanics called multi-body system, that there are two different bodies. One is the rotor, and another one is the tower, and they are connected to some another, but not completely. They are rotating relative to one another. Now, before I do this, I will sketch something on the blackboard. That's why I was looking. So if this is my blades, this is nacelle, this is tower. Okay. Then, of course, once I have the forces, this tower, if I imagine the line along this length, this tower will be deflecting, and I will have deflections distributed along that line. And then I have deflections of the blade distributed along that line. So you can imagine that this is a function of, say, elevations and also a function of time. Rather than, so I have to find those curves at any given time. Rather than looking for the curves, what I will have is, I can select a bunch of points along the tower, and the number of these points I can select. I can call this U1 of t, U2 of t, and so on, UK of t, and final UN of t. And if I am able in some way to find these isolated values at any given time t, then I can plot these values and just knowing these points gives me a good idea how the whole structure deforms. So the whole idea would be now to take the equations that describe this distributed system and transform them to the equations where I will be looking for a certain number of those values only. And there is various ways of doing this. I will mention some of these ways of doing this later, but it has to be done in such a way that those values will really represent the deflection that is continuously changing along the elevation of the tower. So I mentioned part of these difficulties that I have here in that same block system, that there is essentially a need to couple the fluid flow equations from outside and the formations of the structure on the other hand. So because they are coupled, this problem becomes nonlinear, particularly if you consider fluids. Fluids are always nonlinear equations, I described that. And there is a need for some sort of iteration. How these equations look like, I describe on the subsequent slide. And this slide really shows formally full analogy with what I presented for a single block system, single sliding mass. Except that now this M is a matrix. This U that I have is the vector connecting all these unknown displacements as a function of time. F is also a vector that represents a load associated with each of these displacements. And K that I have on the other side is the stiffness, very much like the single spring before. Now it's a matrix. And if I have n of those values, then my M is n by n matrix, U is n-dimensional vector, and K is n by n matrix. How to get to these matrices, this is a little bit beyond this presentation, so we'll leave this out, but you can see a formal analogy, that there is exactly the same structure of the final equations, except that now I have many variables involved, and I deal with matrices. So one way of doing this is so-called the finite element method, where the entire surface of the blade is divided into small pieces, and you can see those pieces on this picture. And then every intersection, every corner where there are certain number of these elements meet, I have an unknown that is displacement. Okay? So this leads to a huge number of equations that I have to solve in time, and that gives me a value of the displacement at every point. Based on those displacements, very much like in the force in the spring, I can compute K times this times elongation of the spring gives me force. Based on those displacements, I can compute all the stresses that I indicated in one of the earlier slides. And then I can use them in any way I want. I can use them to check whether rupture is possible, or buckling is possible, or fatigue is possible. So one of these examples is here. So this is an analysis of a structure like that, which is really a beam, thin wall, very thin, and natural frequencies of that beam computed. So this is the pattern that represents the stresses that you can compute using this subdivision of the entire beam into pieces and then putting it together to form one big matrix equations. Another example is this. So this is a section with the spar, 1 and the 2. So this is one box within another box. And this is for some loading condition and some fixed restraint conditions. This is the level of displacements at certain points. So you can see that there is something going on where this red area is comparing to the remaining part. Here is an example of possible buckling. Right? You can see that for certain level of stresses in the blade, you have some sort of a wavy pattern of stresses and displacement that is a good reason for having a buckling. Now, one can find also deformation. So in this case, this is a deformed shape of a blade. And you can compute, based on this analysis, how this tip moves up and down, how it twists around that, and what are the forces associated with it. This is another example of a structure that looks like a wind blade, divided into finite elements, so-called. Leads to a large system of equations, and then you have a displacement pattern, how varies. So different color represent different value of the displacement. These pictures that I have just presented to you were representative. I haven't done that personally, but now I will give you several pictures that are results of calculations that a master student of mine has done. So this is a beam that is twisted. So it has a longer dimension vertical at that end, but it has horizontal dimensions at that end, longer dimension. This black shape, it's the original shape. So its axis is originally straight, except it's twisted, very much like a blade would be. So we apply the vertical load to this, at the end of this. And this is this color picture is the deformed shape of that beam. There is, for that particular problem, this is the same beam, but it is viewed along the axis. So you can see the beam at the fixed end has vertical cross-section that rotates. As you go along, it becomes horizontal more. And if you apply vertical load, because this twist that you have, the deflection goes not only vertically along the load, but it goes sideways also, a certain amount. That particular problem has an analytic solution based on some simplified theory, but precise enough. And we compared theoretical results with the numerical results that we obtained here in this. And you can see that the displacements are different, but kind of similar. And this pattern of little areas, so that it's a finite element. So that was the same technique used that I was presenting previously for the other results. Here is an example of what so-called I-beam does when you apply a torsional moment to it. Why is that relevant to the wind turbine analysis? Professor Mantel explained, and I also showed you the pictures before, that the blades have internal structure. They have internal ribs called spars. And they have a special material at the top and the bottom of that internal rib. So it really is meant to act like this I-beam. Okay? So in this particular case, you can see that when it twists, it does something strange. And if you look at the beam from the top, you can see slightly that the top flange of it, the top part of it, rotates one direction, while the bottom part rotates in the other direction a little bit. That's a result of the particular response in this case. We computed, again, results and compared to those obtained using some special theory of structural theory, and the error is minimal. Here is another example that kind of resembles the blade, not perfectly because it is probably doesn't have this variation along the blade. But again, we compare the results for using different tests, and these are the numbers. Finally, our ultimate comparison was between the model that we developed, and this is a commercial code. I mentioned some of them later on. There are commercially available programs that allow you to compute structures of that sort. And in our model, we use just 580, which eventually we can manipulate and reduce this to 100 degrees of freedom, 100 values of that sort. Okay? While in this commercial code, we use 14,000 unknowns. So this vector U here at 14,000 because it was for each of those points on this. And in fact, there are 5 numbers associated with each point. And we compared the result for this. and we computed natural frequencies. And in this particular case, mode 1, mode 2, mode 3, mode 4, this is the shape of the structure, vibrating structure with a specific frequency. So we have several solutions, and this is the shell model that we obtain using commercial code, Abacus, very popular commercial code. And this is using our model. And as far as these first few modes are concerned, the result is quite accurate. This is important, and the reason for that is that there are some, I will talk about some commercial software later on that is used in analysis of turbines. They do this kind of analysis to extract modes of deformation, modes of vibration, and they use first 2 or 3 modes for the blade and for the tower in order to build the entire model. So as a result, a good reproduction of these modes allow you to use this commercial software accurately. And this is a dynamic analysis that we've had. So if I look at one particular point, and if I compute a vibration of this is the picture that I see how this changes in time. And there are some equations that describe how that was computed in time. Anyways, we found that there is again a decent agreement between various things. Now, I will be talking a little bit about the commercial tools that are available to solve problems of that sort. And there are commercial tools that are of general application. They can be used in various structural applications, including turbines. But there are also those that are designed explicitly for turbines. And I will mention those efforts as well. Before I do, they're all based on the same kind of concepts of reduction of something that is continuously changing to something that is represented by a certain number of values. This process of going from continuous change to discrete change is called discretization. And late Professor Zienkiewicz, he died a few years back. He was one of the originators of the method that was initiated essentially in the late 50s, beginning of 60s. So software used in first general purpose commercial code. So there are various things. Nastran is one of the huge commercial code that is used for structural analysis, mostly in aerospace industry. There is ANSYS, another code. There are many of them. I don't even pretend to know all of them. One of the most popular one is Abacus, that can be used for all kinds of nonlinear analysis in various applications. But as far as turbines are concerned, then there is an effort in various countries. These codes, some of those codes, are things like turbines or ship or various structures are oftentimes they are insured. And there is a company that uses these codes to verify whether design is safe enough and to estimate what risk they take if they take responsibility for insurance these things. Particularly, Germanischer Lloyd is the company that is responsible for insuring many of the wind turbines. And one of the programs that has been used is this program, Focus, and developed in Netherlands, in Holland. There is also another program, Flex, that is used in the Danish industry. And both of those programs are accepted by Lloyd to make sure that they are not taking too big risk to insure these turbines. In the United States, there is a National Wind Technology Center, which is part of the bigger organization called National Renewable Energy Laboratory. They have developed a lot of different kind of programs that I list some of them that are designed to serve the industry. In particular, they use something that is not based on the finite element that I was talking about, but they have this theory that they call the blade element momentum theory, which is another way of reducing the problem from the continuum to a problem that is discrete, that is dealing with finite number of parameters that you need to find. So as far as National Renewable Energy Laboratory is concerned, they do a lot of different things, but they also develop a lot of programs of special purpose. For instance, this pre-processor and post-processor, which means prepare data for the main program that does the analysis, and then once the output is created, make sense out of this. So use the results and present this in a special way. In particular, they developed a program for analysis of turbines based on this multi-body system dynamics that I mentioned earlier. This program has been kind of looked by the Germanischer Lloyd as a good program, but I think they haven't yet accepted it for really verification of the designs. So these are part of the, this is kind of busy stuff, and you probably have access to these slides so you can read them later. But anyway, what that lists, it lists some of the software that is developed in the National Renewable Energy Laboratory. So TurbSlim, Precom, B modes, and all these other things. So they are used to compute the response of the wind turbine due to various loads. One of the things that they're doing, they're also collecting the data for wind, different parts of the country. They have histograms of different sort, how the load changes due to air flowing around turbines, and that is used as an input to the program. The program that they developed is this one, this FAST. So it is a program that was before known under a different name, and then they accepted this as a standard. The way they do this, in this case, that they compute the frequencies and modes of vibrations for the blades, frequencies and mode vibration for the tower, and then they use a different technique, but based on pretty much similar principles. They create the system of equations that allows them to approximately compute what happens in the tower using just 24 or something unknown functions that they need to find. So this is the software. Now, much of this effort related to analysis of and design of turbines is at Sandia National Lab. They have a special group dealing with wind energy and the design of wind turbines and testing wind turbines. They organize workshops and conferences that includes people from outside of the United States. So this is one example of the announcement of this kind of works. The topics that they cover are quite wide range. Airfoils, this is the shape of the wind blade, turbine blade. And so they still optimize it, the shape, the curvature, the twist, all that affects the, not only that, but I remember when I was visiting Sandia National Lab, they experimented with a slight different orientation of the fibers in the composite materials. And they claim at that point that it looks like they can gain something like 1% more energy just by aligning fibers slightly different way. 1% doesn't seem that much, but given the size of the entire industry, that translates into a very significant amount of money. So this is material part of it. Control, which Professor Mantel mentioned, is working with a professor from Aerospace Engineering Department. Manufacturing, design, analysis, testing, and wind data that is needed to reliably compute what happens in there. That's all I have. If you have any questions related to some of these things, I would be happy to address. So it's an overview. I skipped probably something that is the most critical in this case, how all that is formulated and things like that. But I imagine that for most of you who are not either civil engineers or mechanical engineers, that would be a boring subject. So, plus, it is impossible to cover it that quickly.
The right side of what you took graph.
This one? No, the process of going from here to here, replacing this with from the function, because I have really a function, with the discrete number of values called discretization. Discrete system is the system that deals with finite number of something. Right? So that's. There was a time where personal computers were not powerful enough, and all the work was done on supercomputers. These days, yes, if you have a huge amount of work, it has to be done on a supercomputer. But what I presented here, what we did with my master student, that was on a personal computer. The size was not too big, 500 unknowns, 500 functions to find. So it can be handled by a computer. Even larger problems can be handled these days. Yes, but people are solving problems that range in millions of functions to find, millions degrees of freedom. And then, of course, you have to use not only supercomputers, but special techniques on supercomputer in order to solve. I'm a little ahead of time, but I hope I provided all the essential information that you need or want.